So we depart from the Fisher KPP equation, and we want to prove that U epsilon converge to either 0 or 1. So the method of Evans and Tsuganidis is to go through the WKB method, the of-call change of variable, which changes this problem to a much better looking nonlinear problem, where now the only small term is this one. And what we said is that it is possible to prove that phi epsilon converge uniformly to the function phi, and that the function phi satisfies this. So this is an obstacle problem very related to the variational inequality which was mentioned this morning. So the first thing is to prove the theorem we mentioned this morning. So I will not give a full proof, I will just give the main ingredient, and explain why this of-call change of variable is very useful. That's basically that here the natural estimates are just in L infinity, and that's normal because at the end there will be discontinuities. In this framework, you can prove Lipschitz bounds. So just let me give a proof of Lipschitz bounds in X. So the idea is, so to simplify, I will compute this derivative in one of the direction of space, and to do that, you just phi epsilon at this level is very smooth. You can handle the equation as much as you want, and differentiate and do whatever you want. So you differentiate and you write the equation on the derivative. What you get here is the pi. The other term will give you 2 grad phi epsilon grad pi minus epsilon plus pi, and this term is a little bit dangerous because it depends on U epsilon, but U epsilon is given by this formula, so you can go in there and differentiate. So if you do that, if I am not wrong, you will get minus 1 over epsilon r U epsilon pi, which if you want, you put it on the correct side of the equation to put like that. And because this is a non-negative term, you see that you have just a simple transport and diffusion equation on pi, which means that you can apply L infinity bounds for transport equations, and what you get is that pi of t is certainly bounded in L infinity by pi 0. So if you assume that the initial data is Lipschitz, which we did at some point, then you propagate this information. And that's the same if you want to do it in time. You need a little bit more because you need to assume that initially the time derivative is bounded, which is a little bit demanding for but just technical assumptions. So this is the reason why these functions are uniformly Lipschitz, which prove that I think it was a first statement of the theorem. It proves that you can extract subsequences which converge uniformly locally because you have this Lipschitz bound uniform, and because you have this Lipschitz bound, you can pass the limit in the viscosity sense. So maybe so this I don't so p epsilon so U epsilon converge to U, phi epsilon converge to phi after some sequences, let's say. So that I skip. And the third point is how can you pass the limit in this? So you have to understand what it means to be a sub-solution, for example. So to prove that you have a solution, so phi satisfies the obstacle problem. So that means simply in the viscosity sense, that's easy. That means to check that it is both a subsolution and supersolution. And if I want to check, for example, for the subsolution, I have just put it here. I have to check for subsolution. I have just to take a maximum of phi minus psi and say this is phi minus psi of t0 x0 for a test function psi. And I have to check that these inequalities, the inequalities hold true. So of course, to do that, I have to go back to the epsilon problem, and so there is a trick here, is that you can always assume that this max is strict. And that is because you can always change the function phi with a small parabola to make it strictly smaller, so that now the maximum is strict, and without changing the derivative at, of psi at t0 and x0 in time and space. So just put a small parabola below the function psi to make this maximum strict. So when now you consider the maximum of phi epsilon minus psi, which will be attained at a point t epsilon x epsilon, what you know by continuity, because now you know already that everything converges uniformly, what you know is that t epsilon converges to t0, x epsilon converges to x0. Then what you can do is just use that at the maximum point the derivatives are the same, and so what you obtain is simply from the equation on phi, you obtain that dt psi epsilon plus grad psi epsilon squared, and now at the maximum point the second derivative is negative. So now if you replace the derivative in phi epsilon by the derivative in psi epsilon, you pay it simply by an inequality like that. And that is less than minus r plus minus r plus 1 minus plus ru epsilon. So you pass to the limit, and what you get is dt psi plus grad psi squared. This goes to 0 because now this is the function psi, which is smooth, epsilon goes to 0. And now you get that this is less than minus r plus the limit of this. So now there are two possibilities. Either phi is 0 and this is 0. So if this is 0, if phi of tx0 is 0, is strictly positive, or otherwise, if it's not positive, it means that it is 0, and then that you get that this mean is 0. So in any case, the mean will be 0. So the mean will be negative. So in both cases, that this is 0 or positive or not, you get the inequality in the right in the correct sense for the subsolution. So from that you get the subsolution. If you do the max now, you argue in the same way, and you get and this is of course at the point t0 x0 now, and then you get the other inequality. So this is the reason why this mean and max are very well adapted to these diffusion limits. It works in the correct way. So once you have done that, you agree that that this equation follows by just passing the limit and arguing, as we said, that either this is 0 and phi is positive, or phi is 0 and then the equality here is obvious. So we get the information, we get everything. So there is no more to say about this theorem. The only question now is to understand a couple of things about what it means. And so maybe let me give some remarks on that. So first of all, someone asked the question, but how do you recover the speed of propagation of the interface? So the interface is the interface, now we agree on that. The interface is given by a front u equal 1, I mean, let's say phi equals 0, and phi equals, that's the set phi equals 0, phi is strictly positive. This is what I call omega of t. In this set, u epsilon converges to 0. How can we compute the speed of that? Is there any simple formula for that? Is there a way to do it locally? So the outcome is that it's very complicated, and it's not true that this velocity is defined by any local problem. It has to do with the global problem that you cannot handle but just knowing locally what happens. And to understand that, maybe the simplest is to go back to traveling waves and see what are traveling waves in one dimension. So to see that the speed can be complicated is a non-local problem. We look at traveling wave. So traveling waves are functions which will be phi of x minus ct. Rather than function of t and x, there will be function of x minus ct with c to be determined. So there is a very simple way to build a traveling wave, which is to take phi equals 0 on the left and phi strictly positive on the right. So what we want to find is a traveling wave. So now, because you are moving with the speed of the front, you can fix that the front, let's say, is at the point 0 and the speed is c. So you can look for a function which has a corner here at 0. So this is 0, phi equals 0 here, phi strictly positive here. Okay, so what you end up, so where phi is 0, that's fine, you get your solution. And on the right, for x strictly positive, what you have to write is minus c phi prime plus phi prime squared plus r equals 0. Which gives you the value of phi prime equal c plus or minus square root of c squared minus 4r over 2. And so you see that whenever you give me a speed which is larger than 2 square root of r, so there is a limited minimum speed, c star, which is 2 square root of r, and whenever c is larger than that, you can have a solution. So this slope here is not at all determined by the problem itself. It's determined by the c you give. And because we have to enforce it also at time t equals 0 if you want a global solution, you see that the initial data, phi 0, if you choose it with a certain speed, with a certain slope, will dictate what is the speed of the front. So the speed of the front depends on many things, including, you see by this example, on the initial data. And if you want, so this corresponds to the drawing where u epsilon would be like that, 1 and 0. If you were doing the other drawing that we did this morning, if you were doing the drawing where you have two fronts going like that, in terms of the Hamilton-Jacobi equation, you would have something like that. Here. That would be the viscosity solution of the phi. And then you see that you can have two different speeds depending on the decay at infinity. Okay, and so this is just what remains at this level of the famous theorem of Fisher-KPP equation, that there are traveling waves of any speed larger than the minimum speed, which is given by that. And you decide of the speed by the tail of the distribution. So usually what people like to do is to take a compact support initially, and then you select the solution which is decaying the fastest, and this is the minimum speed. This is the one which remains. All the speeds which are fast go away faster, so the only remaining speed you see is the slowest one, which is this one. Sometimes it's the most stable, but it's not the most stable abstractly. It's the most stable if you consider that all the possible waves can superpose. So here you have the same thing. There is no way to determine simply the solution, except by the fact that it's solution of this global problem. So this is one thing. So there's another thing I would like to insist on. So this is the first remark. And the second thing I want to insist on is that this is an obstacle problem in the sense that this problem has many properties, including uniqueness. So I'm not sure I want to go to that, but you can prove uniqueness for viscosity solution of the obstacle problem. And this has to do with the fact that whenever you will try to compare two solutions, phi 1, phi 2, you will have to take one of the options where either the phi is 0 or this is 0, and the two options will always combine well in with the correct signs to make it go in the direction that you control the difference. So what you prove for that, for example, is that the maximum of two solutions, let's say with two different, the maximum in X, with two different initial data, for example, we always decay. In a weak sense. So you can prove that. And I insist on that because it's not always the case. And I will see, you will see a little bit later. So this closes the discussion on this point of view. But again, this point of view doesn't tell you what happens when phi is 0. So the last question we have to understand is what happens when phi equals 0. And so that's the question, the point number 4. And so here, the theorem or the lemma or the proposition, the lemma is take any open set included in this set where phi equals 0. So take an open set, let's say T0 minus R, T0 plus R multiplied by a ball of center x0 of radius R. Take any cylinder to simplify included in the set phi equals 0. Then u epsilon of tx, or if you want of tx, converge. Okay, that's not a good statement. Sorry, excuse me about that. So the good statement is in the interior of the set phi equals 0, then u epsilon tx tends to 1 pointwise. Okay, so this is the correct statement to do that. So now you really understand that you have solved the problem, because when phi is strictly positive, you converge to 0. When inside this interior, you have pointwise convergence, and of course in the interface there is no convergence because there are discontinuity points. You cannot conclude so easily. There is an easy way to do that, to see that so an easy weak version is as follows. If you come back to this equation and you say that minus R1 minus u epsilon is less than dt phi minus epsilon Laplace phi, because the grad phi is positive. Then if you pass to the limit, and if you look at, so that's the place where the small cylinder comes in this interior, this converges to 1, phi epsilon converges to 0 in the sense of this relation, so this converges to 0. This converges to 0 in this interior, let's call it O, omega of t. So in omega of t. So which means that 1 minus u is larger than 0, if I am correct, and which means in principle it means that u should be equal to 0. So maybe I have made a mistake somewhere. So u is less than 1, implies 1 is larger than u. Okay, so that's the weak version doesn't work. It tells you only that u is less than 1, which we already know. I thought it was better than that. So the argument cannot be like that, because in any case this is an argument which will be only weak limits. These kind of arguments where you neglect things are weak limits and will not give you a pointwise convergence. So the argument is much better and goes to the viscosity solutions. And that's the place where then you introduce the notations. So if you want to really prove it, you have to use the definition of viscosity solution, and then you take this small interval in cylinder inside your set omega of t. And you can take a test function, and the test function I will take is simply t minus t0 squared over 2 plus x minus x0 squared over 2. And of course the maximum of phi minus psi will be equal to 0, which will be attained at the point 0. If you look in this small ball, because there it is 0, everywhere else phi is 0 and psi is negative. So now if you take the max, and it's unique, it's a strict maximum. So if now you look at the maximum of phi epsilon minus psi, it will be achieved at another point, but because always by continuity, because phi epsilon converges uniformly to phi, we know that T epsilon converges to T0, X epsilon converges to X0. You can use this test function in the viscosity sense in this equation, and what you get is that dt psi, which is T minus T0, T epsilon minus T0, plus X epsilon minus X0 squared, which is the gradient psi squared, minus epsilon, dimension of the space, which is the Laplace psi, will be less than minus R1 minus U epsilon of T epsilon X epsilon. Now this converges to 0 because T epsilon converges to T, X epsilon converges to T. So all this converges to 0, and that proves that U epsilon, T epsilon, X epsilon converge to 1. That implies. And because it was a maximum, of at this stage, this implies that U of Tx, T0, X0 is 1. Because it's the maximum point here. And so you get really pointwise convergence at the point T0 X epsilon, T0 X0 to 1. Until you prove the strong convergence up there. Okay, so that's the way you conclude, because of the viscosity solution, that this is true. So what someone also mentioned this morning, but if you really want to study what happens close to 1, I mean, do exactly what you did close to 0, where it's obvious that when phi is positive, you converge to 0. So the idea which was given to me this morning was to say, okay, so that section, why not to look at exponential conversions close to 1? So exponential convergence near for U close to 1. So you could have the idea the natural idea to say that now I set 1 minus U epsilon equal exponential S epsilon minus S epsilon over S epsilon. Because this function is between 0 and 1, I know that S epsilon is not negative, and it's positive if I put it strict. I do exactly the same analysis. I write the equation on S epsilon. The equation on S epsilon is more or less the same, dt S epsilon plus grad S epsilon squared minus epsilon Laplace S epsilon equal R epsilon U epsilon. Because now R U epsilon. So what you do is you have more or less the same equation. What you prove, you have uniform Lipschitz bounds. So uniform Lipschitz bounds just follow exactly by the same method as what was written on this blackboard 10 minutes ago. You prove that. So you can pass to the limit after extraction locally. So S epsilon k converge uniformly to some limit S, and you can pass to the limit in this equation. So what is the limit of this equation? So it is that dts plus grad S squared. So this was the limit. And so this is what? This is always non-negative because U epsilon is positive. And when U epsilon when S epsilon, so we know that S epsilon, so we know that S is positive. And what we know is that when S is strictly positive, when this equality is not true, it's a strict inequality, then we know that this is 0, that U equal 1. And if U equal 1, this means that, okay, so what we know that this is less than R, and what we conclude from the fact that you have a convergence to 1, what you conclude is that you also have an interesting inequality, which is now that when S, so you can write it minus S strictly negative if you want, negative. If F is strictly negative, this is 0. This is equality. So what you can write is that the maximum of minus S and dts plus grad S squared minus R is 0. Is that correct? This is negative, this is non-positive, this is non-positive, and when this is strictly negative, this is equality. So you get that. So you could say, okay, I'm finished, I have a unique S and it's the same. It's not true. This is not an obstacle problem. In the sense that this problem has the right sign here and you cannot prove uniqueness. The problem is not symmetric in 0 and 1. It means the point 0 and 1 play a different role. 0 is an unstable state for this equation, forget about that. For the ODE, 0 is unstable, 1 is a stable point. And this property, this geometric property, whatever, you can change variables as much as you want, they will be kept. And so it's not true that the equations are symmetric. This one of this keeps the feature that 1 should be stable and 0 unstable. So there is no uniqueness, and one way to see that is to take an initial data where S equals 0 in a set like that. So what you can solve always is a real problem where you put an S strictly positive outside. If you forget about this term and if you solve this equation, you can do it, and you can do it because you have a method of characteristics which allows you to give solutions, and what you see is that you have a front which is propagating. So for the real problem, the front is moving, which we know because we know that the front should be moving. By the way, do we know that? Okay, I will show you how we prove it. But you have another solution, which is to enforce that S equals 0 on this boundary, S equals 0 here, and to solve the econal equation outside. So I can fix the set where S equals 0, to fix it once for all, solve the econal equation outside, which I can always do, and then I've got another solution. So these are two solutions that you can build like that, but there are many others that you can build. So this is not an obstacle problem. You cannot have uniqueness. You cannot conclude that the full family converge. It's not so easy. You can prove it, but you need to work more. It doesn't follow from easy analysis. And by the way, this analysis, to complete this program, was done by Barl and Souganidis. Where they prove really that you have a convergence in the correct sense, that there is a unique solution when you know some more information from the left, from the blackboards on your right. So you can conclude the program. And you can prove exponential convergence with the rate S when U epsilon converge to 1. So just two remarks to conclude this and then I will give you some open questions about that. Just two remarks which hold true here. Concluding remarks. The first remark is that we know that dt phi plus grad phi squared plus r is negative. This implies that dt phi is negative, not positive. And this means that phi the set where phi equals 0 will increase. When phi equals 0, it cannot continue to decrease. When phi is positive, it can decrease. And this implies that the set u equal 1 is increasing. So omega of t, the interior, if you want, of this set is increasing. So the invasion front is really progressing. Because this means that phi is closer to 0. Another way to see it directly, by the way, without doing all that, is that you can already divide by epsilon, and you can write dt u epsilon minus epsilon Laplace u epsilon equal r over epsilon u epsilon 1 minus u epsilon. This is a non-negative quantity. This converges weakly the distributions to 0. This implies that in the limit dtu is positive, non-negative in distribution sense. So from the beginning, you don't need to work that much. You know from the beginning that the set that u is increasing, which means that the front is progressing. The front where u equal 1 is progressing again. So that's the same information which is carried by the two formulations. So you know from the beginning that this is really an invasion front. So we see from this analysis that the analysis around stable points by contradiction is more complicated than the analysis close to unstable points. So u is 0 is unstable, but the analysis is fine. So a consequence of that is that you have a couple of open problems. That should be 5 or 5, 6. So one thing you would like to do is to also study other nonlinearities on the right hand side, not only the Fisher KPP, and one of the examples is the bistable nonlinearity. So nonlinearity, which is minus alpha belong to 0, 1. So nonlinearity, which is now like that. And let me call it f of u. You would like to study also what happens in this context, which is usually called Allen-Kahn. And if the problem is not completely equilibrated, which means that the mass which is here is not exactly the mass which is there, this is alpha. If the problem is not equilibrated, we know that there is the two states which are stable, which are u equal 1, will divide the set, the space, into a set where u epsilon is close to 0, a set where u epsilon is close to 1, at least initially it's true, and that this set will be invading with a speed which you can compute from the energy. So the fact that you have a propagating front is also true. We know it. There are different ways to see it. This approach by the Econal equation fails simply because now the unstable point, which is alpha, you don't want to see it. There is no point to make an analysis at that point. You want to have a fast transition through this unstable point in this free boundary. And so you are stuck with an analysis which is only of this type. And nobody succeeded to carry out all the details to prove that a similar result. So this is an example problem which is left open. There is a connected question which is left open, which is a case where these two mass are equal, when the problem this problem is completely symmetric, and the mass here and the mass here are the same. So the speed here of propagation, the sign of the speed, has to do of the difference of mass, equals the difference of integrals, let's call it, in these two regions. If the two regions here have the same area, then this speed is 0. So the front is not moving, so it's not funny. So what you can do then is to make a different rescaling. And this different rescaling if integral of 0 to 1 of f of u du is 0, then you have steady states, many steady states, and what you want to do is to see them moving, so you have to accelerate time. Accelerate time means that you pass from epsilon to epsilon squared. So in that case, the correct scaling, one correct scaling, is simply this, is a fast reaction. Then we can accelerate to see front moving. And in that case, by the way, there have been many studies, and then the case is very well known. By the same type of approach, what you prove is that u epsilon converges to a certain function u, and the function u now is of this type, and the speed here is simply the mean curvature. So and the free boundary moves with mean curvature. And there have been many works on that, and the ansatz is more or less the same. It's a WKB ansatz, but you don't change with the exponential. You use a better better shape function, which is more adapted to this nonlinearity. So you go to a different free boundary problem, which is completely local. That kind of the mean curvature is a local object, and you decide well of the speed of propagation. This has to do with the fact that if you look at traveling waves, so for the Allen-Kahn problem, the traveling wave is always unique. The problem is much simpler than the Fisher KPP because you have a unique speed of propagation. for the Fisher KPP, we say that you have always a minimum speed of propagation, and all the speeds larger will be possible. This is not true for this kind of problems. For this kind of problem, you have a single speed which is dictated by the equation. Okay, so this makes that in fact, this makes that this method doesn't work so well. But again, the conclusion is that even if you use a different ansatz, the free boundary moves with a mean curvature, and you relate that to Hamilton-Jacobi equations. A second order Hamilton-Jacobi equations, because mean curvature is a second order object. So the same strategy works to describe the front through an Hamilton-Jacobi equation.
What happens if the integral is not zero?
So if the integral is not zero, this is too fast. You will not see anything. You have to go to a slower time scale to see a real speed of propagation, because the speed will be non-zero. So already here you see something, and you only rescale time when this front is not moving, because you want to see something moving.
So you have the difference of integral plus a correction due to the curve when you say C.
Okay. If you
next order in epsilon.
If you put C epsilon plus epsilon, yeah. Yeah.
On this problem on the right hand side, what is the initial data for phi?
So phi, you assume that the initial data is of the same shape. So what we did is to assume that phi 0 epsilon is Lipschitz, because we need to estimate to have Lipschitz bounds, and you assume that this converges uniformly to a phi 0, which will be the initial data. So you put it in the initial data.
The problem is given you for the problem, so phi's initial data comes from this limiting u, doesn't it?
Correct. That means that you assume that your initial data are well prepared in that case, yes.
What is the initial data for phi then in the sense?
You make if you want to make it easy, you make it like that. But you can also put it like that if you want.
Yeah.
Which means that you will already decide that there is a place where phi equals 1, phi equals 0, and phi equals positive.
Yeah.
But you don't need to do it. You can.
Well, then the question. So I guess my question comes down to what is it determines the speed of the free boundary?
Again, there is no simple answer to your question. It's a very global, non-local problem, which will see all the solution everywhere.
Is it so? Okay, so given you, so you define phi like this. So it is past the limit in epsilon. The initial data for phi is kind of defined by
or if you prefer, you can also define phi 0 epsilon by if you minus epsilon log u 0 epsilon, or log u 0 if you give an initial data. So if you want to, you can do it. But if you do that, you will have simply an initial layer. The stable regime for that is really u equals 0, u equals 1, or u equals 1, u equals 0. So whatever you do initially, immediately you will come in this regime where u equals 1, u equals 0. So your initial layer will be wiped out very quickly. And so it's very natural to say that you already take an initial data which is well prepared to this kind of shape.
So the question is if I know the initial boundary of phi equals 0,
yes,
then do I need does the motion of that boundary depend upon the shape of phi in the interior?
Absolutely.
It does.
It does.
But it would converge to the stable solution of the perturbation.
It will convert to the unit no, depends on the shape of as we see it in 2D, in one dimension. In one dimension, if I give you an initial data which decays slower than the exponential, then this will give me a larger speed of propagation. So everything is dictated by the initial data, and because you are in multi-D, you can have different speed of decay, rates of decay in different directions, and all this will play a role in the dynamics. It's only if you take an initial data which is compact support that in the long range you will see something which will become spherical, and then then the other question is, now I have this, can you give me what is the limit when t tends to infinity? Okay, and then you see that in the large time everything becomes spherical, and it will propagate with the speed c star if the initial data has the correct decay at infinity. Yes, that's another limit. The other limit, this is becoming completely symmetric, and you see everything. And that's because you have formula. By the way, you have formulas for the solution of this kind of equations with the calculus of variations, and so you can know explicitly what happens in large times. But this is in large times. This is not in the same scale. You have two scales, time and epsilon here. So this is a first example which opened the first class of dynamical problem, dynamical free boundary problems. As a second example, but it's time to okay, it's more or less time to finish. So let me just maybe it's better to let me tell you maybe. So I will begin this thing tomorrow. Let me tell you what I wanted to do in the. I didn't want to spend so much time on this. So the course number. So this is the number 2. I wanted to explain what is the Stefan problem, where it comes from, and what are weak solutions of the Stefan problem, which does, yes?
Ask you this question, are you going to use it tomorrow? Stefan?
Yes, I would.
I will say something in the last talk. If you only need to say what the Stefan problem is.
Oh no, I wanted to show how you derive it, how you construct solutions by an asymptotic, just to do the same thing, depart from a problem at a certain scale. That's the number 3. So that, and then what I wanted to do is to speak of these problems coming from tumor growth, and which are very related to what are models of LHO type in fluid mechanics, which is another kind of free boundaries. So this one, up to my knowledge, doesn't follow in the classification I gave in the first, in the course number 0. This one is a typical example where you can give a nice answer, which is well described by the transport equation, and this is. And there are many extensions of that. There are many open problems also on this subject, which is very much used, by the way, now for medical applications. So this is the next what I want to do in the next courses. Okay, we stop it now. But the questions, we had them before.
Objection.
The question is, this Allen-Kahn model, is there any way that has been presented as the derivation, or is this the way to approach the model? Are there any other derivations? I mean, you sometimes get the model from different points of view. Because then you get the free boundary in the limit.
Yes.
But how did the people in physics derive the free boundary? Just doing this limit?
Alan Khan are chemists or physicists. They observed phase transitions, fast with a very thin transitions, and then they proposed the model to explain it. So there is always, behind these equations, there is always, in these things there are always three scales. One is molecular, discrete if you want. One is the Fisher or Allen Khan. And one is a free boundary. So what we did is only this scale, epsilon tends to 0. This is a number n tends to infinity. And the big question, which have been also looked at very much in the 80s, if you can do like that directly, and if the motion here is the same, if it commutes or not. And the outcome is that usually it doesn't commute. When you do directly from there to there, you have different parameters, and depending on the parameters, you find different answers.
Because you have different ways of taking the continuous.
Yes, it's a two-scale limit if you want, and depending on the two scales, you can have a more richer
Okay.
outcome.
So in this model, you somehow skip the convection term. In some model, probably you have some convection.
Ah, correct. Yes, that's also absolutely. Yes, you can also put a convection.
Similar idea.
If you scale them correctly, yes. Do not remember now, but I think if convection terms look like first order derivative, so you scale them like that. So if you scale them like that, you can do it. Yes. Yes, there have been many variants about that, which have been studied. So you can do. Yeah, correct.
Yeah. So let's thank Benoit again.